Hi guys, welcome to Learn Electronics Repair. So this video came about via some suggestions from various subscribers, to be quite honest. I've been repairing quite a few amplifiers and mixers recently, and a number of you out there said, Rich, you should get a sweep generator. So this is a piece of test equipment that allows you to set up a sweep of frequencies. You can put a start frequency and end frequency, and the device will effectively sweep across that frequency range in a certain amount of time, which you can normally set as well. Having resisted these suggestions for a while, I thought, well, I have a look on PCBWay.com, see if I can find a shared project for an audio sweep generator. And, well, this is what I found. In the shared projects, these are projects that users have submitted themselves, and they get a 10% commission if you build any of the projects, if you order the PCBs from PCBWay or the assembled project. So that's great, nice way for people to make a little bit of residual income. So the first place I came obviously was here, and we have various options on here, audio for example. And here we can find various projects that people have uploaded. There's many pages of these, so the quicker and easier option really is to search for what you want to find. So we can go back into all categories and we can search. And I'll put sweep generator. Let's see what we can find. So sweep generator, and nothing comes up unfortunately. Let's have a look for signal generator. And now we have some signal generators, but looking through all of these various options here, Arduino based signal generator, various other options here, I found that these are either square wave generators, which really have no use for audio work particularly, or not in this context at least, or they are fixed frequency generators. One of the projects I did find on here is this one, the precision low frequency signal generator. This is actually intended for testing subwoofers, subwoofer tester. And this project is actually on my to build list. So here are the PCBs I ordered from PCBWay.com. They always make very nice, very good quality PCBs, you can see. So I have these, and this is on my list, but this is not actually what I'm looking to build at the moment, okay? So I was a little bit surprised I couldn't find one of these projects on PCBWay for the audio sweep generator. I then went to AliExpress and thought, well, maybe I can just buy a DIY kit or just buy one built, okay? And what I found is, although there are some fairly inexpensive DIY type projects or modules you can buy, either they don't have the sweep facility or the radio frequency ones, or they're expensive if you can find one that does have this feature. So I didn't really find here what I was looking for. And I thought, well, you know, you can do this another way because I've done it already, and that's to use free software or an online signal generator. So here we are in Google. Most of these items, I've had a look through them, are either expensive or they're just signal generators. They don't do this sweep of frequencies, yeah? But there are free online generators that will do this. I mean, here's one, I've used this before, and you can see with this you can put in a start frequency and you can put in some end frequency, some duration, choose a sine wave, and it uses a sound card in your PC. And that is an audio sweep. But you'll notice it doesn't stop at the end. You can click on this continue playing tone after sweep is finished. If you take that off, it just stops. Okay, so this one and one or two others I found will do this, but only once at a time. Like the programmers forgot to put the button that says repeat. Yeah, I mean, what were they not thinking? Yeah, but anyway, we do have these sort of options, and some viewers said Audacity and other software programs will do this, or you can create an audio file with this sweep in, repeating. And I agree with you, you can do all of those things for free without any additional hardware and just use your PC or laptop as an audio source. You can do it. I'm sure when I was a kid I would have loved playing with this thing, yeah. But the problem is, although you can do that, basically, it's pretty useless. And the reason it's useless is because when you're repairing something, you have your amplifier, okay. In the input, you want to put your sweeper frequency, so you're starting from a low frequency and getting higher and higher, and it's so difficult to draw this. Okay, like that, frequency increasing. And you probably want to take your oscilloscope somewhere down here, and you want to have a look on your scope to see what the signal looks like. The problem with this is, how do you synchronize your scope so you can see the way the circuit responded across the frequency range? Because you probably want to know, is it amplifying at the low end only, the high end only? Is it amplifying equally across the whole range? Is there some areas that are not working? Imagine you're working on a mixer where the tone network isn't working, something like that. So you need a way so you can look on your oscilloscope to see how the circuit is responding. And this took me on a little bit of a journey. So the journey started really back on YouTube, and the guy a lot of you will know of already, IMSAI guy. And IMSAI guy actually built an Arduino based sweep generator, and we can see it here attached to his scope. So what he's doing is, into the circuit he's feeding a sine wave starting at a low frequency going up to a higher frequency, and this is showing how the circuit is actually responding to that sine wave at different frequencies. Now, to do this, as I mentioned, you need to be able to synchronize your scope, and what he's actually doing, and he'll show you in this video and I'll link it, is that he's actually built a little Arduino based circuit. Okay, this one here, we can see it. And it's effectively playing back a sine wave which is stored in memory at ever increasing frequencies from the lowest to the highest. But it also, on one of the output pins of the Arduino, generates a sync pulse at the start of the sweep. And he's using that sync pulse on channel 2 on the scope to trigger the scope. And you can see here he's showing you how he's doing this. So this effectively is a sync pulse, and from that he knows where the sine wave starts. But you notice with his Arduino, first of all, he only has 8 steps in the sine wave, so that effectively is a sine wave at a low frequency. It looks like a staircase, yeah. And the second thing he found is that he couldn't get this thing to run at very high frequencies. It was very limited in the frequency, the fastest it would run. And he's also generating a sine wave that only has 16 steps, 8 going up, 8 coming down, basically. So it's a very low resolution sine wave as well, and he still can't get a high enough frequency out of it to make it useful. The reason for that, which he explains, and you can watch the link video, is that the digital to analog converter in the Arduino is too slow. It can only operate at a certain speed. But that set me on the route. So from there, I actually had a look to find a microcontroller based circuit that uses parallel digital to analog converters rather than serial that operates faster. And that brought me to another really famous guy, so let me show you. This is what I based my project on. And this circuit, which I will link in the video description, you can have a look at the original project. This one was by Kerry Wong, who's a guy who pops up quite a bit on YouTube. So this is another one of these SWIP generators. He's using an ATmega 328P and a parallel input DAC. This one, DAC 0800N. Now the great thing about these and these is you can get both of these chips in a dual line package, so you don't have to have them in the little QFPs, which are hard to solder. These are very inexpensive, and the same with these. In fact, you can see you can get the DAC for, well, you can get 10 of them for €1. They're very cheap. And the processor works out about €1.50 or something like that. The other main parts of this are on the output. So we have an LM358, again extremely cheap, and you can get them in dual inline, easy to solder. And we have a few resistors, a few capacitors, a crystal. And that's about it, to be quite honest. You could probably substitute the bare chip with a crystal for a little pre-built module probably, but I decided to go with the chip and just use the dip package, and that can just plug it into an IC socket. Okay, we have a variable resistor here which sets the frequency range. We have a switch which sets the sweep tap to be linear or logarithmic. Okay, and he's using this one, I out, to drive into the op amp. This sets the gain signal level, so that's your signal level, and out comes the audio. And from here, out comes the sync pulse. So every time the processor starts a new sweep, it generates a positive going sync pulse, and we can use that to synchronize our scope. This, therefore, is useful. One of the features of this DAC is it has two outputs. So you have out and overscore out. Overscore means active low, and this is actually the inverted version of that. So it's upside down. So if we get a sine wave coming here, we get the upside down sine wave going there. And I thought that might be quite useful if we want to test things like class D amplifiers, so we can feed an inverted signal in to the output stages if, for example, there's some other fault that stops the built-in signal inverter from working. It just seemed it might be useful, never know. And all we really need is an extra LM358 and an extra pot, and that's it. And we can have two outputs, one inverse of the other. So I based my design on this one. And here it is. So this is basically the same circuit. We have the processor section. We have the DAC section. And then we have the two outputs, so out and out hash. And we have two output stages. So out feeds into this one with a level control, and out hash, which is the inverse, feeds into this one with level inverse and output. So those are your two output stages. Here we have the sync out, the frequency range, and the switch between logarithmic and linear. So that's the basic design that I've come up with. This is the original project that I based mine on. You can see the circuit there. That's what I've printed out. Okay. The source code is here, so that gives us something to work with, because I think we can probably modify this as well and maybe improve the frequency range of this by making some changes. So Kerry does mention that the sine wave this generates has 256 steps in it, not 8 like the IMSAI one guy has. So this is much more an accurate sine wave. He also mentions that you can increase the frequency response by making it 64 steps in the sine wave, which is something we can play around with when we get this built, and let's have a look to see how well that works. But ultimately with this, the maximum frequency range will basically depend on how fast the MCU can send digital data parallel and how fast the DAC can respond to that and set the output voltage at that step. Because they're not instant, there is some delay. So this chip is quite an old one, it's been around a long time. The MCU, I'm sure there are far more powerful ones available. So it may be possible that by using a faster MCU and a faster DAC, we can up the output frequency maximum quite a bit. Again, that's something we can explore. But at the moment, let's get the prototype PCBs made so we can put this together. Then on a future video, we can play around with this. We'll get it built. We'll see how it works. And we'll look into the options of improving on the design of this. It would be nice to get this thing up to 20 kilohertz max or something like that. At the moment, I believe it's just several kilohertz, but Kerry didn't actually say so. Let's find out. So now we need to design our PCB layout, create our Gerber file and order our PCBs from PCBWay.com. So let's do it. And here is our PCB. It's quite large. I didn't really try to make this thing very small. I needed the space for the various connectors anyway. The actual connectors will be mounted off the board on the front panel. So these are literally just points at which I can solder. This is the switch which selects logarithmic or linear, and I have the control knobs for the level and the frequency range. We can see the CPU, we can see the DAC and the op amps here, and this connector has the various power supplies on. So this requires a plus and minus 5 and a 12 volt. We could use a little module, in fact we could stick it over here on the board somewhere probably to generate all those voltages. But in true ghetto style, I'm going to run this from an old ATX power supply when I first try it. And let's see how well this actually works. Bear in mind, this is a kind of like development or proof of concept. Detlef and myself were chatting today actually about how we can improve this, how we can make it faster. But first we need to see how fast this actually operates on its own. So let's create a Gerber file. Let's upload this to PCBWay.com. Okay, I have my Gerber file, so we're back at PCBWay. Let's order some PCBs. This is quite simple to do. We go to PCB Instant Quote and we go to Quick Order PCB. Simple as that really. Add the Gerber file. Open. It's just a zip file which was created by the software. It's found our PCBs there. Just green PCBs with white silk screen. We could have something different. Red is of course the channel colour if you like. So we'll go with red with white silk screening. This image doesn't actually change, but the PCBs will arrive in the colours we requested. And there we are. So this is now waiting PCBWay to check that to make sure everything is okay. Then I order my PCBs and they will arrive shortly. A nice thing about this is I've used the DIP IC, normal standard IC. Same as this one on this Arduino. So that's the actual processor, so I can fit that onto a socket on my PCB. This is a standard 16-pin DIP as well, so again it's in a socket. And if you look, these connections are really connected to the processor. The only connections between the processor and the DAC section are just these 8. And then we have the 2 outputs. I'm actually using both outputs and 2 sets of the output interface circuitry, the analog circuitry. So it makes this easy to use as a development board once it's all put together. If we want to use a different type of processor, for example, we can do so. I can stick some pin headers into the socket here, that connects to there, and then we can just effectively put another processor. We can take this one off the board, we can wire another one in just there. So that's something we can try. Another thing, the original software uses a table of data in the EEPROM to store the waveform, the shape of the sine wave. DLF thinks it's probably faster to use a array in RAM effectively on the processor, so we can try that. There's a number of things we can do with this to see how much speed we can get out of it. But a lot of that, of course, will depend on how fast it is to start with, and Kerry didn't specify how fast this thing will run. So let's wait till they're here, let's get one built, and then let's do some interesting experiments with it. Okay, so I hope you enjoyed that. You'll be seeing this shortly on my bench when the PCBs and the DAC is here. I've got the other parts already. So if you've got any interesting suggestions, what we can do with this, how maybe we could improve this, get into the comments here below, and when the stuff arrives we can try them out. Okay, thanks for watching. I look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.